Hello, my dear students. Today we're going to talk about second order optimization, and the classic example is a Newton method. And firstly, we'll start with the problem formulation. Now we have second order information from the oracle, which means that given any point xk, the oracle will tell us all information about the function up to second derivative, which means that we can get the function value, the gradient vector, and the Hessian matrix. Note that we'll consider the problem of minimization, the function which maps from vector space of dimension n to a scalar, and this problem is what we're going to solve here. And as I said, the classic example of this method is the Newton method, and we'll start with the intuition behind the Newton method. And geometrically speaking, it can be viewed as follows, and it can be derived from the problem of finding roots of a scalar function. Imagine that we have a function, let's say phi from x, and our goal here is to find such x's that brings phi to 0. So x star is a root here, and our goal is find a root, not a minimum here. And suppose we are starting with some point, let's say xn, and here we have the function value, and we can construct local Taylor first order approximation of our function, and we can denote it as phi with a high index 1, which means first order estimation, and with the lower index xn from x, which is actually nothing else but phi from xn plus scalar product of, say, phi, derivative of phi from xn multiplied by x minus xn. That's the linear function from x. You can verify it. We have only this dependence from x, and this function is linear, and the slope of the function is phi, derivative of phi, the first derivative, right? And here we have f, but that's just like the question of notation, doesn't matter here. And we'll find a point where this linear function goes to 0, which means that our next step will be the root of our linear approximation, phi 1xn. And this iterative procedure of finding roots of local linear approximations of our function under some assumptions will lead us to the true root of our function. So which means that next time I'll build this first order approximation and go here, it will be xn plus 2 and etc. Then I'll go somewhere here, and actually I will be already close to a solution. That's it, and let's again verify the formula for the method itself. And as I said before, at any point x plus delta x, we can write a linear approximation of our function phi from x, and it will be phi from x plus this linear term on delta x. And as I said before, we are looking for the root of our linear approximation, so we take this and setting it to 0. And here we have the step value, which you're going to need to take to go to the root of our linear approximation, right? That's it. Which means that iterative procedure will take the following form. And actually, that's the Newton method. For finding roots of a function. But imagine now that our function phi will be derivative of f. And we are to find the roots of our function phi or the roots of derivative. But the roots of derivatives are actually critical points of our function f from x. Which means that our target and our goal here is to find the critical points using the same procedure. And here we can state that derivative of phi is nothing else but the second derivative of f in a scalar case, right? And here we have the following procedure, just a simple substitution here. And we know that in a scalar case, we can write actually this formula, right? But imagine that f function is a vector function, which means that it takes a vector as an input here, and we cannot divide by a second derivative if second derivative is a matrix. That's why we're placing -1 here as a degree, right? That will be just inverse matrix. And actually, that's the exact formulation of the Newton method for function minimization. Again, that's the Newton method for function minimization. These methods are closely related to each other. Actually, that's just like the one method, but for different purposes. And what is interesting here is our goal initially was to find a critical point. Note that this condition is only necessary, but not sufficient, which means that there are some points which satisfy this exact formula, but they are not the minimums. Which means that actually you should be careful when applying Newton method for function minimization, and next intuition will provide like more information about it. Also, we can derive a Newton method from another perspective, and this perspective is second order Taylor approximation of the function. And again, imagine that we have a function f from x, which is orange here, and we can build a local second order parabolic approximation of our function, which will be called, let's say, f with this wave from x, but this approximation is built around xk. That's why we have xk here. You know, we can like write down exact parabola which are locally the best second order approximation. And Taylor gave us the formula for this specific purpose. And this formula will be the following, which is pretty important. And you can see that if we'll just leave the first two terms here, you'll obtain the first order Taylor approximation as it should be, right? You can just increase it, like you can write down third order, fourth order, and etc. But now, like, we're stopping here. Okay, what's interesting is if we have this second order approximation of our function, what will be if we go to the minimum of this parabola? So we just exactly state that xk plus 1 will be like, I want to say the minimum, but it will be fair to say that that will be also the critical point of our parabola. Which means that I have to say that the gradient of f with wave at this point is equal to 0. That's it. Let's take a derivative of our function with respect to x. And note that this term doesn't depend on x, which means that it will shut down to 0, right? And this term is actually a linear term on x. We have just some multiplier here, and here is the dependence, the linear dependent term. And this term is a quadratic term. Here, this is the second derivative of our function, which is a matrix. This is a vector. This is also a vector. And as far as our Hessian is symmetric by definition, because like by construction of Hessian matrix, it should be symmetric. This means that the derivative of our quadratic term here will be the following. We'll have only the gradient here, so let's numerate it, right? That will be like the 0 term, first term and second term, and that will be derivative of the first term and the second term. We have a 2 and 1 over 2, which will multiply and will give us 1 as a scalar here. So we have already something which looks like a Newton method, but let's derive it like in a fair manner. I'll focus on two formulations here, and they are both pretty important. If you multiply on an inverse of a Hessian here, so you just multiply of f a Hessian inverse both left and right, you'll get the exact formula for the Newton method here. But as I said before, this formulation is actually more important than this. This is just like the exact formulation of the Newton method, but we'll later discuss why the first formulation is more important and more interesting for us. Okay, and it's interesting that this way to derive, to get the Newton direction is coincide with the previous idea of finding critical points using Newton methods for root finding, right? And the procedure will be the following. You'll just build a local quadratic approximation and you'll go to the minimum. And here at the new point, you are to build new quadratic approximation, which is presented here, and etc. and again. That will be iterative process until some convergence. And the obvious problem here is that if your function, for example, is not convex, let's imagine it will be something like, I don't know, like this. That's your function. And you, let's say, starting from this point, or let's even more close to the maximum here, at this point here, that's your starting point x0. So which direction would you choose if you go if you run Newton method here? you'll approximate locally with the best parabolic approximation, and this approximation actually will be like this. It will be a parabola, but with a minus sign because of the slope here, because of the curvature. And as far as your function is not convex, these situations could happen here, and which means that your next iteration, x1, will be actually not a direction of descent, but the ascent direction, right? And actually your iterative procedure will converge to a maximum here. So that will be like x star for a Newton method. And that's not what we want from the optimization method, but that's the idea which we have to keep in mind when we are using plain or like vanilla Newton method. There are some special ideas how to deal with these problems. We'll discuss it later. So again, we build local second-order Taylor approximation of the function and go just to the minima of this approximation and repeat it again. But note that if the function is not convex, your approximation could lead you to the ascent direction, not the descent direction, but that could be a problem. And let's take one more look of how quadratic approximation is similar to the actual function value when you are far from the optimum. Here you can see an animation, and a red point here stands for the current point where we build a quadratic approximation. Red line stands for the quadratic approximation, black for the function itself. And green point here is the minimum of the quadratic approximation. And you can see that for this specific function, if you are far from the local minima, quadratic approximation works really bad in terms of the optimum of this quadratic approximation is really far from the real target optimum. And you can even take a look if, for example, you are somewhere here at this wall of your function, the new point will be higher in terms of the function value itself. That's again bad. But the function is convex. So the function is convex, but Newton direction will be still, could be, however, it's interesting, am I right? No, it couldn't be. A decent direction for the convex case? No, I mean, sorry, the convergence will be just slow in terms of the convergence of, that if your function is convex, but the Hessian is degenerative, at some point you'll have problems with Newton direction, right? Because for the calculation of the Newton direction, you have to inverse a Hessian here, which means that here, for example, at the minimum, our function looks like a parabola, but at the corners, our function looks pretty linear. And for sure, for linear functions, the Hessian will be degenerate, or the determinant of the Hessian will be 0, or it will not be invertible matrix here, right? That's the problem. Imagine that you have a function, let's say f from x is equal to just x. The second derivative is just 0, so you have to divide by 0. That's one more problem of the Newton method itself. Okay, we say some things about the problems of the Newton method, but for what reason we could apply this method if we have only problems here, right? So let's take a look at the convergence of the method itself, and we are also want to show here you some more animations. That's the counterplot for a function which has two minima on the left and on the right and on the left of the picture, but also it has a local maximum here. And let's take a look of the field of directions of different optimization methods here. So the gradient direction here, can I pause it? Actually, yes, I can. Just a second. Yeah, that's it. For example, let's take a look at the ideal optimization method field, which means that, sorry, again, here are two local maximums here, right, which are white, and that's the global minimum here, right? This function is not convex, but that's the case for the most real-world problems. And ideally, from any point, we should go directly to the global minima, right? But that's not always possible. And for example, for gradient type methods, let's take a look. Here, we're always going to the descent direction. So starting from this maximum, we goes to the like orthogonally to the contour lines here, and we're going to the minimum here. But what's going on with the Newton method itself? And here we can take a look that around local maximums here, we are going to them, not to the local minima, right? And again, let's take a look at the animation. That's the ideal word. That's like the gradient field, and that is a Newton field. But what's interesting comparing to these two methods here is the convergence speed of Newton method. And here's the proof of convergence for those of you who are interested in like strict derivation, but I'll go directly to the conclusions here, and the conclusions are following. If your function is strongly convex function, so let's take some like direct assumptions on the function behavior. Your function should be strongly convex first, so that not just the convex function, right? That should be at least faster and faster than some parabola, right? Not, for example, a linear function or a modulus function. Moreover, your Hessian of the function should be Lipschitz continuous, which means that for any points x and y, the difference of the Hessian in norm should be bounded by some constant m multiplied by the difference of the vectors itself. That actually means that your Hessian could not change rapidly or like instantly, right? If you plot the graph for the second derivative for the scalar case, it cannot be like this, because here you have immediate changing, where like that's not the Lipschitz continuous, right? It can be any other type of changing, right? But not this instant changing. So again, we have Lipschitz continuity constraint here on the Hessian, not just for the gradient or the function value, but for the Hessian, which also means that if your Hessian is Lipschitz continuous, that means that moreover your gradient will be Lipschitz continuous and your function will be Lipschitz continuous. And again, we have this property where this L is actually a mu, which is strongly convexity constant here. And actually this is L is a Lipschitz constant for the gradient. Is bounded by this. Then Newton method will converge quadratically, which is actually super fast, right? But this convergence will have a local behavior, which means that we have only local convergence here, which means that if we are close to the solution, then we'll converge super fast, like insanely fast, which means like actually quadratic convergence means that you're doubling your accuracy in terms of the number of correct digits in decimal representation, which means that if you have like one meaningful digit, next iteration you'll have like 2 digits after the floating point, next iteration will have 4, 8, and etc. So you'll always have like several iterations of these methods to converge to very accurate solution here. So again, if your function is strictly convex and the Hessian is bounded in terms of Lipschitz continuity, the Hessian is Lipschitz continuous, then Newton method will give you quadratic local convergence. And local here again stands for some region, and this region is defined actually by the constants of strong convexity and Lipschitz continuity here. This L is just mu here. That's it. Comparing to the gradient descent, this convergence is much faster, but this convergence is a local one, and we saw it. Actually, we saw that if you are far from the minimum, you can have some difficulties. And actually, typically, Newton method will give you superlinear convergence speed, again comparing to the gradient descent, which can give you only linear speed of convergence for strongly convex functions, right? That's interesting. That's what we have to know about the Newton method. So what's very good about the method? This method have quadratic convergence. And quadratic convergence, as I said before, is insanely fast. We'll see on examples a little bit later here. Also, it's nice that this method, due to design, has affinity invariance, which means that if you scale your space by some affine transformation here, the sequence of function values will be the same as for the non-transformed case. So again, you're running Newton methods in two spaces. One is like the default space, some Euclidean space, some starting point, and the second space is the linear space after some affine transformation. Your Hessian will also be transformed, your gradient will also be transformed, but the function value sequence will be the same. That's what is called affinity invariance here. What's also interesting here is that you actually don't have a lot of hyperparameters here. but you need to calculate Hessian. So again, we don't have, by default, we do not have any learning rates here or something like this. But in fact, we have, and we'll talk about it a little bit later. What's the problems with the Newton method? We have to store Hessian matrix, which requires n squared memory, which is bad. But what's even more, we have to solve linear system. And by linear system, what do I mean? Here, as we've seen before, we have this iteration of the Newton method. But in fact, no one invert like a Hessian directly, but typically we're calculating the following thing. Let's denote this direction as Newton direction, the nu. And what's interesting here is that, again, the nu is equal to x k plus 1 minus, let's write the following way. It will be x k minus x k plus 1, right? Or we can multiply by a Hessian matrix both two sides here, and we'll have this equation minus gradient here and Hessian at the point multiplied by xk plus 1 minus xk, and xk plus 1 minus xk is actually let me verify it. So we have okay, sorry, let me like take a wider bracket here. So minus Hessian multiplied by gradient will be in Newton direction, which means that this Newton direction is nothing else but the difference of k plus 1 and k point here, and this difference is actually here, Newton direction. And that's the problem of finding a solution for linear system, because that's the matrix n times n, that's our target vector, which we are going to find here, and that's the right hand side. And actually we're solving linear system here, and by default general linear system will require n cube operations, and sometimes it can be speeded up. For example, if your matrix has some very strict structural form like diagonal matrix or block diagonal or upper triangular or something like that, or I don't know, Fourier matrix or Toeplitz matrix, and etc. And that's actually the main idea to think of how Newton method should be implemented. It's just a solution of a linear system, which is this. You have always a matrix, which is a Hessian, and the right-hand side, which is an anti-gradient here. And the solution to the linear system is the Newton direction. So as far as you'll find this solution, you just write this xk plus d Newton. That's it. The problems also, like the next problem here is, as I saw, the Hessian can be degenerate at the solution or close to the solution, and it will affect the convergence, and we'll see how. But also interesting that, for example, as I said before, if the Hessian is not positively defined, this direction could be not a descent direction. For example, when you have, as shown before, this behavior, right? That's here Hessian is not positively defined. That's why we have this ascent direction property here. Okay. And how can we deal with these problems? First of all, we can try to think of the Hessian matrix not as a general dense matrix, but as a matrix which has some special structure. And that's actually the key to the quasi-Newton methods, which are trying to build some reasonable approximation of the Hessian matrix using the first order information about the function. So, which means that we are trying to build a good estimation of the Hessian using some combination of our first order local information. And we'll talk about it a little bit later. That's the one possible direction to go to deal with the problems of the Newton method. And there is one more interesting idea which is often applied when we are talking about the Newton method. That's what is called damped Newton method. Let's write it down here. What is damped Newton method? That's the classical Newton method, but with some additional hyperparameter which is called step size here. And typically this hyperparameter is chosen with some linear search procedure, like Goldstein-Armijo conditions, like backtracking, like golden search, and etc. So step size is usually chosen by backtracking or line search. And actually, this generalization of the Newton method could make a convergence of the Newton method a global one, which means that for some functions, if you apply a Goldstein-Armijo backtracking procedure for the damped Newton method, your convergence will not be local, but the global one. That's pretty important for the convergence property. And again, this damped alternative of the Newton method is well used in practice. Okay, let's take a look at some visualizations here. Okay, here we'll take a look at the Newton method behavior for the function x to the power of 4. And on the first look, we have okay, nice convergence, method works, it goes to the minimum. What's the problem here? And the problem could be seen if you'll plot. Okay, let me first run it. That's it. That's a fair execution. Yeah, that's it. We have the same convergence here, and that's the graph for the function, the residual in function value, and it's okay on the first on the first look. It's pretty okay. We have a convergence here, but the problem here is that this type of convergence is obviously linear because we have a line on the logarithmic plot. That's bad because such type of convergence could be obtained using a simple gradient type method here. And the problem here is that the Hessian becomes more degenerate here, and here at the very optimum the Hessian is not invertible here, and here the Hessian is just a number, and this number goes to 0. We cannot divide by 0. That's the problem with the convergence. It slows down the whole idea here. It's slowing down. But let's take a look at another example of the function which doesn't have this problem. And here we have, like, again, some convergence. And what about the convergence plot here? Now we can see what is called quadratic convergence, and you can obviously see this very fast procedure, which means that we have only like few iterations, like 4 iterations, just to go, or even 3 actually, right? If the 0 iteration stands for the beginning of the procedure, we have only like 1, 2, 3, okay, let's say 4 iterations here, and have an accuracy which is close to the 10 to the power of -8. And you can see that at each iteration, your residual is like going faster and faster to the minimum. That's what is called quadratic convergence on the logarithmic scale, right? That's okay. And here we don't have this property of degeneracy at the minimum. But what if we'll start our procedure somewhere far from the optimum here, which will show us the local nature of the convergence of the Newton method. Let's start, for example, from 1, 0, 5 here, and let's, for example, plot for 10 iterations. What we obtain here is, yeah, for 10 iterations we have numerical result out of range here. Let's decrease the number of iterations slightly. You can see a divergence here. That's because, as we said before, if you are far from the local minima and your function is not strongly convex here, or you are not using some step sizes here, you'll face these problems with convergence. And for example, what's for the residual here, it increases like a lot, right? That's why for 10 iterations here we would like going out of the floating point accuracy. Let's compare these methods for the problem of what is called analytical center of the set, and we'll describe it in the seminar in more details here. Again, let's run it here. We're installing some library which has optimization methods implementation and a lot of quasi-Newton methods here. Okay, again we have the function which have this form, which is a sum of logarithms, and geometry of this function will be presented on the seminar, so don't miss it. Here we have the Newton method. Again, we have a gradient. Let's take a closer look here. We have a gradient of the function, we have a Hessian, and we're solving a system with the Hessian as a matrix and an anti-gradient as a right-hand side here. Also, we're applying line search procedure, which make this Newton method as a damped Newton version, right? Line search is implemented using, as far as I remember, golden ratio algorithm here. Okay, let's verify it here. Yeah, we have Armijo backtracking here, and let's plot the convergence. Okay, it was already here. Yeah, there it is. And here's the difference between the Newton method behavior and gradient algorithm, which justify the difference of the complexity of each step size here. So what do we have here? We have a norm of the gradient plot, and the closer you are to the critical point, the smaller the norm of the gradient you have. And for example, here we can see a linear convergence for the gradient method, which is good actually, because we are using a correct step size procedure selection, and the same for the Newton method actually, and the quadratic convergence of the Newton method. And actually that's cool. That's pretty okay, because you can see that like for very small number of iterations here we're just going to the minimum. And you can see an interesting detail here is previously, like starting from the beginning of our simulation, for several iterations we do not have a quadratic convergence, we have a linear convergence here. But then, as we are in like this region of quadratic convergence, we are going for like several iterations to the very minimum of the function. And this is done because of the due to linear search step size selection procedure. Let's try what if we'll use like a constant step size here for the Newton, for example. Let's compare it. And here we have a Newton method, but yes, that's actually that's this method is actually implemented in what is called Newton method here, but we are calling this direct calling from the library. I don't remember how to call a constant step size here, so let me just remove the step size selection procedure, and I'll take a look. No, I have a step size here. Okay, let's set it as a constant. Will it work? No, I have to use a sign function. Okay, I'll try to verify it. Okay, I can stop a constant step size now. And for example, for the Newton method, we have a constant step size, which is equal to 1, which stands for the vanilla Newton method. And for the gradient method, we'll like set something like this very small step size, and we'll take a look at the behavior here. Actually, we can see that we have a huge gradient norm for the gradient method. Let's take a look. Probably the step is too high here. Yeah, we have something like very big norm of the gradient after the first iteration here. So let's like decrease the step size here, and let's take a look on what's going on here. Still we have maximum iteration limit, and still have huge gradient. Let's decrease step size more. Yeah, we have smaller norm of the gradient, which is okay, but still you can see a difference, right? And even in Newton method, works quite well here, and still it goes from the region of the superlinear convergence to the region of quadratic convergence here. Okay, what's about like more iterations here, and with a smaller step size. Oh no, with the same step size. Yeah, we've decreased a little bit the function value, and yeah, you can see the difference, and you'll have to tune it right manually. That's a problem. And again, if you return to the Armijo backtracking, which were the default here, you'll have a better results, and that's why backtracking is so important in real practical problems. Yeah, you can see the difference. Okay, that's it. Next important theme is quasi-Newton methods, which are trying to address the problems of Newton method itself. And let's sum it up a little bit, what we have for the Newton method. Very fast quadratic convergence, affinity invariance, and in the linear case, we have no hyperparameters, but in fact, we'll have this damped Newton method with the convergence, with the step size selection procedure, which is typically some backtracking ideas. But what the problems is, we have a problem if your function is not convex, or like locally not convex, or the Hessian is not positively definite. That's a problem. And a lot of computational power should be spent on calculation of a single Newton direction on each iteration. You have to solve a linear system here. And you have to store the matrix itself. And this is why Newton method is not so widely used in nowadays machine learning problems, when the n number is typically something like thousands of millions or even a billion, because if you have, for example, 10 to the power of 8 or 10, n square will be 10 to the power of 16 to 18, or like 20. That's not feasible for like most of the computers which we have today. And what's about the number of iteration, it's even more, it's n cube. That's the problem. But quasi-Newton methods will try to address this problem and to address these issues by significantly reducing the complexity of solving linear system, and we'll take a look at them. And the overall idea is to use some approximation of Hessian matrix. For example, let's formulate our quasi-Newton method as follows. We have like a step alpha k and sk as a direction here, and direction sk will be typically computed as follows, where the matrix bk will stand for the inverse Hessian, which means that if you use the exact expression here, that's just the Newton scheme, Newton method. But our goal is to find something which tends to the inverse Hessian, but a little bit easier to compute. So we have some iterative procedure here. For example, we can initialize B0 from some invertible matrix, let's say I, which is identity matrix here, and then apply these like iterative modifications of the matrix itself in order to be close to the inverse Hessian here, and which are, which specific kind of closeness between bk and inverse Hessian will be here is the following. Let's consider this Taylor approximation, right? That's actually, what does it mean? It means that the difference of the gradients between iterations should be somehow related to the Hessian and the difference of the vectors itself. So like in scalar case, it will be like f derivative of f from x minus derivative of f from y divided by x minus y should be somehow close to the second derivative of f, right? Or at y, because that should be when x is close to y. Yes, that's it. So that that could be expressed in the following way. We can multiply by inverse Hessian here, and we'll have fxx, which stands for the Hessian here, xk plus 1 minus 1, which stands for the inversion, multiplied by the difference of the gradients, should be somehow close to the difference of the points here. Okay. Okay. I thought that I can zoom it, cut and paste. Yes, now I can. Okay. That's it, and that's just the bk plus 1 here. So we can express it as follows, that the difference of the axes should be close to the difference of the gradients multiplied by the bk plus 1 here. Actually, it could be a bk, that doesn't matter like a lot, but for building a procedure, we can use bk plus 1. And if you just write what is bk plus 1, which is bk plus delta bk, we'll have the following rule for the delta bk. Okay. And the next will be like, what if we make some additional assumptions on how this delta bk should look like? For example, let's add at each iteration, let's add some rank 1 update. Reasonable, simple, okay? So what if we look for the delta bk as this expression, where mu is some scalar and qk is some vector, which means that if qk is some vector, you'll have this qk and qk transpose, and you'll have a matrix which has rank 1, which is called outer product of these two vectors here. That's like, again, n times 1, 1 times n. You'll have as a result n times n. Okay, that's it. We'll just substitute this form of delta bk here at this expression, and like let's call it b approximation, right? B approx. And we just substitute b approx here, and here what we have is mu k qk transpose multiplied by delta yk should be equal to delta xk minus bk delta yk. That's it. So we just substitute it, and what do we have here? Mu k qk transpose qk delta xk minus bk times delta yk. We just have like a possible, one of the possible, yes, I forget to multiply it by delta yk here. And it's interesting, if we'll take a look, here we have a scalar, right? You have a scalar, and that's a vector, and that's a vector. And one like possible solution here is that what if mu k will be qk transpose times delta yk minus like inverse, which means that this whole expression will be just 1, right? That's possible. That's pretty possible. Sorry. That's, again, that whole expression will be just 1. And about qk, so it will be just equal to this, right? So qk will be equal to delta xk minus bk delta yk. And what's interesting here is that what do we have as an input here? At each iteration, we have here. So here we have this delta xk. We have also previous version of inverse Hessian here, and we have a gradient difference also as an input here. So all these terms are known to us. And after qk calculation, you can compute mu k as follows. So I have like a formula here, and if you just place it here and make a simple calculation, you'll receive a general formula for inverse Hessian update here, which is delta bk, which can be calculated using only first order information. And what's interesting is that you've just built a simple quasi-Newton method here, which is called typically SR1 or symmetric rank 1 update. Or sometimes it's called Broyden method also. So again, you have Q transpose multiplied by mu, which is this multiplied by delta yk, right? That's it. And interesting that this method will work for some cases, and we'll even see the comparison of these algorithms. The next idea, okay, what if delta bk will be not a rank 1 update, but, for example, a combination of 2 rank 1 updates? That's it. What's interesting here is that if you have this like special structure of your matrix, you can calculate this expression pretty reasonable. For example, which means that at each iteration you will only need not a cubic complexity, but a squared complexity, because you'll just only need to multiply this by this. Or we can even calculate the following thing. Let's take a look. Minus bk plus delta bk multiplied by a new gradient, which is known here, and you can just write here. But okay, sometimes you can treat this term as a like term from the previous iteration, but you have a problem that the point of the gradient should be also a new point. But still, you can like formulate a version of quasi-Newton method which somehow reusing previous information for the direction computation, right? That's possible. And interesting that, okay, if you'll say that let's find update in this form, Okay, you can repeat the previous ideas just like completely, and you'll receive general form for Dividend-Fletcher-Powell method, DFP. But okay, if you take a look at the update in this form, which is two vectors q1 and q2 and some symmetric matrix U to catch them all, you'll have what is called like well-known BFGS algorithm, which is called like for the after surnames Broyden-Fletcher-Goldfarb-Chanot method, and that's it. That's just like the different version of finding this update form, right? And let's take a look at the comparison of these methods. That's it. For example, yeah, we'll take a look at the following problem, which is called analytical center problem, as it was before. This problem is actually like, imagine that I have a set of linear inequalities here. And, oh, sorry. Yes, that will be, this notebook will be on the seminar. Let's take a look at the Quasi-Newton benchmarking, which should be presented in our PDF. Okay, let's continue on this version. And what the problem here is, imagine that I have a set of linear inequalities, and additional constraint on an absolute value of each component of x vector here. And actually, this is, geometrically speaking, nothing else but finding at center of this polyhedra, which is defined by these inequalities. And you can like write down these logarithmic barriers here, and that means that you'll have an optimum point which is equally distributed from all the borders here in some sense. That's why this problem posed in this form. Okay, and let's take a look at the direct comparison here. Here, for example, the comparison of Broyden method, which is called BB1, actually is just, as far as I understand, okay, it's actually the variation of gradient method with some heuristic on step size selection. So BB1 here stands for the like one good heuristic actually for the gradient method. So all these methods are of a first order, which means that they do not know any information about the Hessian directly, but they all try to estimate the curvature using the first order information here. And here we have Davidson-Fletcher-Powell method, BFGS, and one more modification of BFGS with limited memory, which is also quite good, quite well known like for practical performance here. And let's take a look at another idea here. Yes, that's an ill-conditioned system, and here are the, for example, gradient descent algorithm, which is this line here, which you can see this direction, which is like pretty understandable here. And here are different like blue line here stands for this, right? Gradient descent with some heuristic on step size selection, so it's like kind of quasi-Newton method, but actually it also looks like a first order method. BFGS algorithm and some modification of them for example, here and here. And actually, if you go through our link of presentation here, this is a link to Quasi-Newton methods benchmarking. Yes, for example, for logistic regression problem, you have something like this. Actually, this is BFGS with limited memory, which is green. Trust region method is some modification of the Newton method. And actually, I don't know what is TNC here. Just don't know. Yes, there are some, like, it's interesting that, like, for different problems, different methods like behave differently. That's obvious, and you have to compare them. And what's interesting here about the time spending on the iteration here is that, like, the fastest method here is BB1 or BB2, which are quite the same, and because they are only computed the gradients, like just a single gradient on the iteration, and like some simple heuristic on step size. That's why they are like fastest in terms of the iterations. But what's interesting about, for example, David and Fletcher Powell method and BFGS method, we can see that, for example, in this picture, yes, let's take a look at this picture. Like, the fastest method was the gray one, which is LBFGS from SciPy. And yeah, we can see these, like, this meaning for milliseconds here. And what's interesting here is that's a comparison of iteration complexity. But what's really interesting here is time complexity. And you can see that despite the fact that BFGS method outperforms in terms of the number of iterations here, these BB1 and BB2 methods, which are just a gradient descent actually, they are spending less time for the general procedure because each iteration is a little bit cheaper for them. And the same idea for, like, this, but here we have a gradient descent which takes more than BB1 or BB2 because of the incorrect step size choosing selection. And you can see that, for example, correct implementation of BFGS outperform gradient descent in terms of time, which is important here because like, that's obvious that it should outperform in terms of iteration, but each iteration is a little bit more expensive than the gradient one. So in general, you can see this trade-off between complexity and speed, right? That's it. Okay. Thank you for your attention. Goodbye.